Case study and discussion. Donya Eugenia River Basin, coordinates 22 degrees 46'55" S, 43 degrees 25'44" O, drains a watershed of 18 square kilometers situated in the Rio de Janeiro metropolitan area, crossing two cities of a lowland region called Baixada Fluminense, Nova Iguaçu and Mesquita. Donya Eugenia River is about 10 kilometers long. The first 4 kilometers are located in Nova Iguaçu inside an environmental preservation area called Jarachino/Mandena. The subsequent 6 kilometers run through the city of Mesquita, crossing a dense urban area until its outfall at Sarapuí River. The preserved upstream area contrasts with the degradation found in the lower urban area, just a few kilometers downstream, and is a reference for restoration goals. The climate is hot and humid with a summer rainy season, all in the Köppen climate classification. It has an average annual temperature of 22 degrees Celsius and an average annual rainfall of 1,700 millimeters. Mesquita has approximately 170,000 inhabitants, according to the 2010 Brazilian census and the Human Development Index calculated for the city and reported by the United Nations Development Programme in 2010, is 0.737, which places Mesquita at the 850th on the list of Brazilian municipalities. The city has many infrastructure problems. According to REF, in the most populated areas of the city, there are numerous shantytowns built illegally, without considering environmental risk factors, both in flat flood-prone areas and on steep hillsides. Even in areas regularly occupied, urban growth was not controlled, urban occupation sprawled, open areas are few and infrastructure was not adequately provided. The main problems of this city can be summarized as follows. Intense and irregular informal settlements on riverine areas. Lack of vegetation in the urban reaches of the river. Urban settlements in risk areas, including dwellings on river banks, where the houses act as dikes, canalizing the river. Parts of the main river run canalized underground. Recurrent problem of flooding, which affects about 80% of the city population. Sedimentation at various points of the river. Discharge of sewage and solid waste into the river, with visible environmental degradation and health hazards. Scarce infrastructure. Degradation of the urban environment. In the recent past, the municipality has canalized Donya Eugenia River towards its upstream reaches in an artificialization process that is stressing the environmental protection area, while configuring a loss of opportunity to integrate the river as an environmental asset in the urban landscape. The consequences are clear: less biodiversity, fewer open green areas, less leisure opportunities, greater environmental fragmentation, with consequent degradation, and worse floods downstream. In the context of the discussion developed in the previous sections of this lecture, this case has motivated a research joining the necessity to find a flood control alternative, the aspiration to revitalize the degraded urban areas and the goal to improve environmental conditions. The main part of this research is concerned with the reorganization of the open spaces system, providing a storage capacity to the urban drainage system, while using the river path as a corridor to integrate environment fragmented areas among them and with the upstream protected forest. A mathematical hydrodynamic model, MODSL, developed in the Federal University of Rio de Janeiro, UFRJ, was used to produce flood maps and then evaluate flood conditions. Due to the limited availability of data, the model calibration used the results of a previous study as reference. This study was carried out by the Rio de Janeiro state government, in the revision of the Water Resources Master Plan of the Iguaçu-Sarapuí River Basin. The catchment's outlet was one of the control points adopted for calibration purposes. At this point, the target discharge was 40 cubic meters per second, and the modeled value reached 41 cubic meters per second. To ensure a greater reliability, the calibration process also reproduced critical flooding points, based on historic events and population memories. The diagnosis of the current situation considered as a design storm event with a 25-year return period, as recommended by the Ministry of the Cities, in Brazil, shows the flood map obtained for this situation, confirming the criticality of the flooding problem in Mesquita. The mathematical modeling showed areas with inundation levels reaching more than 0.75 meters in some places. The critical points are associated with the city center region and in riparian areas with informal settlements. This antagonistic situation shows that both formal and informal urban areas suffer from significant flooding. The region located upstream the railway line is also critical, once the railway walls act as a barrier to runoff and urban storm drains are insufficient. Current situation, flood map, recurrence period 25 years, source, see ref. It is important to note that some flooding observed in the current situation is due to the lack of minor drainage in the basin. Thus, floods are retained in the plains and cannot reach the river rapidly. The city center is greatly affected, both major and the minor drainage system fail. The plains near the river, at the city center and a natural wetland downstream, where some informal settlements appear, show the highest flooding levels. An interesting observation related to a past situation helps to illustrate the discussion. In the beginning of 1970 decade, only the area upstream the railway was urbanized. Past situation, 1970, source, see ref. Mesquite population, according to IBESH census for 1970, was 93,678. Considering that soil imperviousness is proportional to the population density, it was possible to simulate floods in 1970. Taking the same rainfall event of 25 years of recurrence period, flood maps simulated for 1970 were compared with the ones obtained for 2010. Two main observations arise from comparing these maps. In the downstream areas, where no urbanization took place, there were no flooding problems. In the upstream area, although with fewer people and less imperviousness, floods were already significant, even if less important than today. This means that the space that should be occupied by flood flows was inadvertently occupied by the built environment. Current and past, 1970, situation, flood maps, recurrence period 25 years, source, see ref. Flood control is a matter of allocating spaces. Flood flows need space and the open spaces system of a city can be used to fulfill this aim. After completing the flooding diagnosis, an alternative has been studied to solve this problem, with the expectation of avoiding river overflows and organizing major drainage demands, using the open space system to reorganize flow patterns, but also providing river improvement and urban revitalization, increasing both natural and built environment values. This alternative combined river restoration, RR, solutions and sustainable drainage, SD, techniques, acting through the spaces provided by the open spaces system. In this alternative, RR plus SD, the river was analyzed and divided in three stretches in the urban area, identified as different landscape units: an upper reach near the natural protected area, Area 1, upstream, a central area in the core of the city, Area 2, middle reach, and a wetland in the river outfall, Area 3, downstream, as schematically shown in RR plus SD alternative, source, see ref. All the three areas suffer from informal settlements, substandard habitations and flood risks. Taking into account that it is a consolidated urban watershed, the open spaces shall be considered with multifunctional characteristics, landscaping, recreation, biodiversity and flood control, for example. The design project proposals are listed in Table 1 and Figures 6 to 9 show the concepts supporting the proposals. The total storage volume offered by the three areas, in the combined RR plus SD alternative, sums approximately 270,000 cubic meters, with additional contribution of infiltration measures and on-site detentions, adding 106,000 cubic meters. Control urban occupation, diminishing urban density. Avoid increasing imperviousness. Escalate a set of different park typologies to allow a smooth transition between the city and the upstream green areas. This way, the park set in the sequence of the controlled urban growth area should begin with urban equipment, then becoming green, possibly exploring fruticulture, as an economic possibility for the local population, until reaching the protected environmental area. A fluvial park, along the river course is also proposed. This park will begin here, connecting the upper forest to the city, and it will continue throughout the watercourse, crossing the city from one end to another. Continue with fluvial park, opening space where possible or necessary. Relocation of the houses that are directly settled on the river banks, giving space to the river. New housing typologies must be explored, using multi-floor buildings on stilts or pilotis. Fluvial parks store temporary floods. A number of soccer fields, public squares and free open areas near the river shall be incorporated in the blue-green way that is being created. These areas will also assume multifunctional characteristics, helping in the flood control. The fluvial park finishes in a constructed wetland. The houses settled in a very low elevation should be relocated.